This PowerPoint presentation is from the National Council of Teachers of Mathematics Annual Conference. The session models each of the Common Core State Standards for teaching fractions in 5th grade in both area models and on the number line. It's the third of a series of lectures modeling fractions in 3rd, 4th, and 5th grade, and is recorded by author M.W. Penn. The Common Core State Standards for building an understanding of fractions are found under the domain Mathematics, Number and Operations, Fractions. In Grade 5, they teach 4 elements: the addition and subtraction of any fractions, covering those with different denominators; the division interpretation of a fraction, which, for example, translate the fraction 1/5 as 1 divided by 5. They cover the multiplication of any fractions and also simple cases of division of fractions. As we continue our study of fractions in Grade 5, we should remind children what a fraction is. A fraction is a number. Fractions answer the same question all numbers answer. As Square Bear would put it, how many you got? I got 4 puppies. Bear has 4 legs. I got 72 on the test. I got 2/3 of the pie. I got 7. 7 what? Number doesn't tell us what. Number just defines quantity. The Common Core State Standards begin Grade 5 using equivalent fractions to add and subtract fractions. The first standard of Grade 5 reads, add and subtract fractions with unlike denominators by replacing the given fractions with equivalent fractions in such a way as to produce an equivalent sum or difference of fractions with like denominators. The example given in the standards is 2/3 plus 5/4, which equals 8/12 plus 15/12, and the sum is 23/12. The algorithm for performing this operation is the quantity AD plus BC divided by B times D. In other words, we're to find a common multiple of the fraction's denominators, replace the fractions with equivalent fractions having this denominator, and then use these fractions to add or subtract fractions with like denominators. Because we will begin our study using equivalent fractions to add and subtract fractions, we might revisit equivalent fractions. In Grade 3, we created area models for equivalent fractions. The area models show that equivalent fractions cover the same portion of a rectangle. In this slide, we see the area models for 1/3, 2/6, 3/9, and 4/12. We see that 2/6, 3/9, and 4/12 are all equivalent to the fraction 1/3. And at the bottom of the slide, we see that 1/2 is equal to 3/6, or 6/12. Because both thirds and halves can be expressed as equivalent fractions with the denominator 6 or 12, we might use 6 or 12 as a common denominator to add or subtract thirds and halves. But again, children have been familiar with this concept since 3rd grade. As a simple example of equivalent fractions that share a common denominator, let's begin by adding the fractions 1/4 and 2/3. How would we add fourths and thirds? Well, we would first find a common multiple of the denominators 4 and 3, and then use this common multiple as a denominator for equivalent fractions that share this denominator. We see that both fourths and thirds can be equivalent to fractions that have 12 as a denominator. At the bottom of this slide, we have the area models that show that 1/4 is equal to 3/12 and 2/3 is equal to 8/12. When we add 3/12 and 8/12, we find that the sum is 11/12, expressed in this area model. The algorithm given in the Common Core State Standards simply provides a formula to do this. We see the sum AD plus BC divided by BD. In this case, 1 times 3 plus 2 times 4 divided by the quantity 3 times 4. The sum is 11/12. Children are familiar with the number line model, and they've been working with them for several years. They know that they can join two segments on the number line to find a sum. And because a fraction is a number, they can use the number line to add fractions. In this example, we will locate the unit fraction 1/4 on the number line. We can then locate 2/3 on the number line by finding the unit fraction 1/3 and counting 2 of them. When we join the segments 1/4 and 2/3 together on the number line, the answer, the sum, is 11/12. In this slide, we model the example given in the standards in a number line model. We find the lengths of the segments 2/3 and 5/4 and join them together to find our sum of 23/12. We see that the denominator of the sum is 12. Using the algorithm, we come to the same conclusion. But once we begin to demonstrate this concept on the number line, the reason for finding a least common multiple and using it as the denominator for equivalent fractions makes more sense to children. We can continue to use the number line model to stress this concept. Looking at the number line, we can ask children what fractional parts of a unit can be equivalent to both thirds and fourths. If we divide the unit into segments of 1/12, we can see that both thirds and fourths fall in the same place on the number line, which means that thirds and fourths can be expressed in fractions equivalent to twelfths. By comparing many different fractions on the number line and finding equivalent fractions with different denominators, children will become familiar with the concept that equivalent fractions with different denominators have denominators that share factors. When we ask questions such as, can a fraction with the denominator of 7 be equivalent to a fraction of 1/2? Or can a fraction with the denominator of 14 be equivalent to 1/2? And ask them why, they should be able to discover that only fractions with denominators that share factors can be equivalent. And of course, we can always go back to the area models. In this slide, I'm adding only 1/3 and 1/4 in an area model. 1/3, of course, is the equivalent fraction of 4/12, and 1/4 is the equivalent of fraction 3/12. And you can see that we can add 1/3 and 1/4 in an area model. The number line model is at the bottom of the slide. In this slide, I took the actual example from the standards and visualized it in both an area model and on the number line. I didn't extend the number line to 23/12. The numbers were getting rather small. But you can see that using number lines or number line tapes marked with many unit fractions allow children to visualize addition using equivalent fractions with like denominators. Hopefully children are now moving away from visualizing the concept in area models. Subtraction is simply the reverse. In this slide, we are subtracting 1/4 from 1/3. We do it in an area model at the top and on the number line below. In the area model, we divide a rectangle into 12 equal parts, and we subtract 1/4, or 3/12, from 1/3, 4/12. In the number line model, we simply count backwards. Remember, though, that these are just visual representations of the algorithm, and children must begin to use the algorithm. This presentation focuses on modeling fractions, but these models are simply visual representations of the computations involved. In this case, the computations are finding equivalent fractions that share common denominators, and then using these fractions to add or subtract fractions that initially have unlike denominators. The models are used to explain the validity of an algorithm, but children must learn the algorithm. So the next standard asks us to solve word problems involving the addition and subtraction of fractions that refer to the same whole, but that have unlike denominators. It also offers two suggestions. First, use visual fraction models or equations to represent the problem, and use benchmark fractions and number sense to mentally assess the reasonableness of the answer. The example they give is that 2/5 plus 1/2 should not result in an answer of 3/7, because 3/7 is less than 1/2. Number sense. And remember, a fraction is a number. If we look at this example from the standards on the number line, it's clear that 3/7 is to the left of 1/2, and therefore a number of lesser value. Some students might still visualize this concept better in an area model, but use area models only if needed. At this point, we must stress number sense, computation, and the algorithm. At this point, students should be able to find a common denominator and to locate fractions on the number line. So all of this should now be a review, but the number line does provide an easy visualization of fractions with different denominators. This standard, though, stresses word problems, and it's our job to try to create word problems based on things that really interest children. Characters from stories they're reading, plots of current movies, sports cars. In this slide, Roundhound orders pizza. A pet saves some of his dinner for a late-night snack, and Alien Bob learns about ice cream. It's always our job to make math fun. Okay, now that we understand equivalent fractions and the reason for finding equivalent fractions that share common denominators when we want to solve problems of addition and subtraction, the standards move on to multiplication and division. First, the standards ask us to interpret a fraction as the division of the numerator by the denominator. In other words, to understand that the fraction a over b is equivalent to a divided by b. They ask us to solve word problems involving division of whole numbers that lead to answers in the form of fractions by using visual fraction models to represent the problem. The examples given in the standards are first to interpret 3/4 as the result of dividing 3 by 4, using the practical problem of 3 units divided by 4 people, so that each person receives 3/4 of a unit, and to note that 3/4 multiplied by 4 equals 3. Secondly, if 9 people share a 50-pound sack of rice equally, how many pounds will each receive? These standard area models and number line model are a visual representation of a fraction as a numerator divided by a denominator. Here we divide the whole into 3 equal parts, or thirds, and we see that 1 divided by 3 equals 1/3, and 1/3 times 3 equals the unit. So let's use models of this type to solve word problems involving division of whole numbers, leading to answers in the form of fractions. Let's use the example given in the standard. Interpret 3/4 as the result of dividing 3 by 4. Let's use both the familiar area model and a number line model to interpret a written problem. In this problem, Eileen Spinelli's beloved character, Mr. Hatch, has 1 brownie, but he would like to share it with 2 friends. We see that each person will get 1/3 of the brownie. We see it interpreted on the number line and in the area model. But always write the equation. 1/3 times 3 equals 1, and 1 divided into 3 equals 1/3. Harry Potter would probably be more interesting for 5th graders. Suppose we have the problem of Harry and 3 of his friends sharing 3 vials of magic potion. How much of the potion will each of the 4 friends receive? This is a very interesting visual model of the problem. 3 vials, a large measuring cup, and then 4 smaller cups to receive the portions for the 4 friends. But it might be kind of messy. Here we see a number line model and, if necessary, an area model for the same problem. And of course, we have the equations. 3 divided into 4 parts equals 3/4, and 3/4 times 4 equals 3. In this slide, we look at the second example from the standards. If 9 people want to share a 50-pound sack of rice equally by weight, how many pounds of rice would each person receive? And between what whole numbers does your answer lie? At the bottom, we see a number line model for the problem. 50 pounds divided into 9 equal portions means that each portion would weigh 5 5/9 pounds. And 9 times 5 5/9 equals 50. Ask yourself, would an area model be helpful here? Well, in this slide, we do have an area model for 50 divided into 9 equal parts. You can see that area models become less viable as numbers become more complex. The 4th standard on fractions in 5th grade asks us to apply and extend previous understandings of multiplication to multiply a fraction or a whole number by a fraction. The first section of the standards, 4a, asks us to interpret the product a over b times q as a parts of a partition of q into b equal parts, equivalently as the result of a sequence of operations a times q divided by b. They ask us to use a visual fraction model to show that 2/3 times 4 equals 8/3, and to create a story context for this equation. And then we're to do the same with 2/3 times 4/5, which equals 8/15. In general, A over B times C over D equals the quantity AC over the quantity BD. This may all seem rather complicated, but remember that in grade 4, students have already seen the multiplication of a fraction by a whole number, and we've modeled it on the number line. Remember this standard? Understand a fraction A over B as a multiple of the fraction 1 over B. And remember that 1 over B is a unit fraction. On the number line, we can see the fraction 2/6 and view it as a multiple of the unit fraction 1/6. In the same way that we visualized 2 times 1/6, we can visualize 2 times 2/6 and 3 times 2/6 here in their equations and on the number line. Before we begin studying multiplication by fractions, it might be wise to pause and instill a little number sense. Remember Square Bear and his question, how many you got? Well, in this case, it might be wise to ask, how many of what do you got? Suppose we multiply 1/2 by 4. Well, what does that tell us? It tells us that we have 4 1/2s. We have a half, and a half, and a half, and a half. We have 2. But 2 is less than 4. This is not what children expect when they do a multiplication problem. Suppose we multiply 2/3 by 12. Well, what have we got? We've got 2/3 and 2/3 and 2/3 and 2. We have 12 2/3. Well, that doesn't add up to 12, does it? No, 12 2/3 equals 8. Again, something children are not ready to expect. Now let's look at the algorithms given in the standard. 1/2 times 4 equals either 1 part of a partition of 4 into 2 equal parts. That is, 4 divided into 2 equal parts equals 2, and you have one of them. Or you have the result of a sequence of operations A times Q divided by B. 1 times 4 divided by 2 equals 2. Children must learn to use the algorithm. So let's begin modeling them. So let's return to the algorithms and interpret the product A over B times Q as A parts of a partition of Q into B equal parts. In this example, AB is equal to 8/4. We've taken 8 on the number line and divided it into 4 equal parts. And in the multiplications, we have 1 part of this partition of 8 into 4 equal parts. We have 2 parts of the partition of 8 into 4 equal parts. And we have 5 parts of the partition of 8 into 4 equal parts. Now let's look at another example of this interpretation. 6/7 times 9 means that we have 6 parts of a partition of 9 into 7 equal parts. Using this interpretation, 6 times 9 divided by 7 equals 6 times 9 sevenths, or 54 sevenths. I've taken a 9-gallon tank of water and put it into an area model, partitioning it into 7 smaller tanks, knowing that we will have 6 of them. Using the algorithm, 6/7 times 9 equals 6 times 9 divided by 7, or 54 sevenths. 7 and 5/7. And you can see this not only in the area model, but on the number line below. The algorithm for multiplying a fraction by a fraction in the standards reads that the fraction a over b times the fraction c over d equals a times c over b times d. Let's look at the algorithm for multiplication of a fraction by a fraction. In this example, a over b is 2/3, and c over d is 1/2. AB times CD will equal A times C over B times D. 2/3 times 1/2 will equal 2 times 1 over 3 times 2, which equals 2/6, or 1/3. But to instill number sense, we might think of this multiplication as answering the question, how many you got? Square Bear might ask, how many 2/3 do we have? Well, we don't have a whole 2/3. We only have a half of 2/3. 1/2 of 2/3 is 1/3, and we can see this on the number line. The next standard, 5NFB4B, takes us into the realm of tiling with unit squares to demonstrate that the areas are the result of multiplying the lengths of the sides, even when the numbers are fractions. It reads, find the area of a rectangle with fractional side lengths by tiling it with unit squares of the appropriate unit fraction side lengths, and show that the area is the same as would be found by multiplying the side lengths. Then multiply fractional side lengths to find areas of rectangles, and represent fraction products as rectangular areas. To demonstrate this concept, let's use an area model. Here we have an example of a unit square and a square with a fractional side length of the unit fraction 1/2. You can see that the unit square is tiled with 4 1/4 inch squares. A square with sides the length of a unit fraction 1/2 is also tiled with 1/4 inch squares, but it's tiled with only one of them. This may be difficult for children to conceptualize, so it might be best modeled by considering what happens to a rectangle of any size when the side lengths become smaller. Luigi is selling his world-famous pizza with all the toppings for $20. In this slide, you can see that the pie measures 20 inches along each side, and though it's very popular, it's much too much pie for some people. So Luigi decides to sell a smaller pie. He makes a pie that measures 10 inches along each side, and since Luigi figures it's half the size of the big pie, he decides to sell it for half the price. The simple area model, though, demonstrates that the pie is actually only 1/4 the size of the original pie, and Luigi is going to have to sell it for 1/4 the price. In 5NFB5, the standards finally interpret multiplication as scaling or resizing by comparing the size of a product to the size of one factor on the basis of the size of the other factor, without performing the indicated multiplication. As Bear has always said, we have to recognize how many we got. 5NFB5B reads, explain why multiplying a given number by a fraction greater than 1 results in a product greater than the given number, and explain why multiplying a given number by a fraction less than 1 results in a product smaller than the given number. Operations with fractions initially lead to confusing results for children because differentiating between multiplication and division is troublesome. They have come to expect that division results in a smaller quantity, and multiplication results in a larger quantity. It's what they expect to see. Of course, operations with fractions often lead to the opposite results. So, when multiplying with fractions, if we ask the question, how many do we have? They can see and understand that often they have less than the initial quantity. 3 times 2 means that we have 3 2 times. But 1/3 times 2 means that we have 1/3 2 times. 1/3 and then another 1/3. The result is less than 2. This approach often makes more sense to children. In this slide, Square Bear compares the products of several different multiplications without actually performing the operation. But he can determine quite quickly which product is going to be less than, equal to, or greater than the other. The last part of this standard relates the principle of fraction equivalence to the effect of multiplying a over b by 1. Children, of course, have been familiar with the identity property of multiplication for several years. And now the multiplication of fractions tells us that any number multiplied by n over n has the effect of multiplying that number by the identity property. Because n over n is equal to 1, n over n times any fraction a over b yields an equivalent fraction to a over b. And this concept is illustrated on the number line diagram at the bottom of the slide. The standards now ask us to move the multiplication of fractions and mixed numbers into real-world problems. It's our job to create problems from the real world that children live in, from the world of sports or pets, apps or fantasy. But you know your class, and you choose the problems you create. When creating problems for your children to solve, remember an important thing is that the children find them interesting. So what are your children interested in? Suppose they're reading Stargirl. Give her half a square of lovely melty chocolate and say that she perhaps wants to give 1/4 of the 1/2 to her pet rat. Or maybe Harry has a half a vial of secret rosewort. He's mixing a magic potion, and 2/3 of the 1/2 vial spills on the table. Baseball, skiing. We must create problems that will entertain our children because math is fun. The standards now ask us to apply and extend previous understandings of division to divide unit fractions by whole numbers and whole numbers by unit fractions. 5 NFB 7A asks us to interpret division of a unit fraction by a non-zero whole number and to compute such quotients. For example, create a story context for 1/3 divided by 4, and then use a visual fraction model to show the quotient. The standard further asks us to use the relationship between multiplication and division to explain that 1/3 divided by 4 equals 1/12, because 1/12 times 4 equals 1/3. A visual example might be 1/3 of a cake shared equally among 4 people. What fraction of the whole cake will each person receive? And remember that students may need a great deal of practice to see the connection between the visual representation and the more abstract equations. The best visual fraction models of this division would be area models. So in this slide, we divide 1/3 of a large sheet cake equally among 4 people. We have a visual representation of the cake in an area model at the bottom of this slide. We can see the whole cake divided into 3 sections, or 1/3, and then one of the 1/3 divided into 4 pieces. Each person receives 1/4 of the 1/3 of the cake. But what portion of the entire cake does each person receive? And we can see in this area model that they receive 1/12 of the entire cake. At the top of the slide, we see a number line representation of 1/3 divided into 4 equal parts. The next standard asks us to interpret division of a whole number by a unit fraction and to compute such quotients. For example, create a story context for 4 divided by 1/5, and to use a visual fraction model to show the quotient. They further ask us to use the relationship between multiplication and division to explain that 4 divided by 1/5 equals 20, because 20 times 1/5 equals 4. At the bottom, we have the simple visual model for 1 cup of milk divided into half cups. How many half cups are there in 1 cup of milk? In the second area model, we use the example given in the standards. We have 4 units divided into 1/5 of a unit. How many 1/5 of a unit are in 4 units? A simpler visual fraction model for this might be to take 1 unit. How many 1/5 are there in 1 unit? Well, of course, there are 5. If there are 5 1/5 in 1 unit, how many must we have if we have 4 units? This is a good time to revisit the problem of differentiating between multiplication and division when we're using fractions. We see that the result of dividing 4 by 1/5 is 20, a larger number than 4. But what we actually have is a greater number of smaller pieces. To address this, as we did in the last slide, I like to begin by dividing a unit. If we divide a unit into 1/5, we have 5 pieces. 1 divided by 1/5 equals 5, a larger number of smaller pieces. The final part of this standard, 7C, and indeed the last standard on fractions in grade 5, asks us to solve real-world problems involving division of unit fractions by non-zero whole numbers and the division of whole numbers by unit fractions, using visual fraction models and equations to represent the problem. The first example given is how much chocolate will each person get if 3 people share 1/2 pound of chocolate equally. And the second example asks how many 1/3 cup servings are in 2 cups of raisins. Let's take a look at the first example. How much chocolate will each person get if 3 people share 1/2 pound of chocolate equally? Here we have modeled this in both an area model at the bottom and on the number line. In the area model, we see that we have 1/2 pound of chocolate, and we've divided it into 3 equal pieces. We've done the same thing on the number line, dividing 1/2 into 3 equal parts. 1/2 divided by 3 equals 1/6, because 1/6 times 3 equals 1/2. The second example given in the standards is how many 1/3 cups servings are there in 2 cups of raisins. And I've modeled this both in an area model and on the number line. When we're working with unit fractions, it's easy to divide a unit, and it's often the best way to begin a problem with children. In this slide, I've given a number of examples of problems for first dividing a unit fraction by a non-zero whole number, a half a yard of cloth used to make 2 aprons, a third a gallon of milk divided between 5 kittens, or for dividing a whole number by a unit fraction, 24 quarts of ice cream divided into third cup portions. Just make the problems interesting to your children. When you create these problems, though, remember to include your children's interests. Use a character from a video game, or a character from a book, Alien Bob, Mr. Hatch, Octagonopus. Use a pet or a school mascot. Remember, it's our job to make math fun. And that's it for the 5th grade standards. I think we have that covered.